Welcome back to Basic Electronics. We have looked at a synchronous counter in the last lecture and worked out its state transition table. We will now look at the reverse problem, that is, given the state transition table, how do we design a synchronous counter which follows that table. We will then look at how two counters can be combined. Okay, let us begin. Let us now discuss how to design synchronous counters. We start with this transition table for a JK flip-flop, and here we have taken a positive edge triggered flip-flop, so therefore these active clock edges are shown to be positive edges. Alright, so what is this table about? It says that if we have J equal to 0 and K equal to 0, then our Qn plus 1 is going to be the same as Qn. If we have J equal to 0, K equal to 1, then our Qn plus 1 is going to be 0, and so on. Now, when we talk about design, we need to consider the reverse problem. That is, we are given Qn and we are given the next desired state, that is Qn plus 1. And then what should J and K be in order to make this happen? That is the question we ask. Let us take a specific example. Let us say our Qn is 0 and we want our Qn plus 1 also to be 0. Alright, how can we achieve that? We can do two things. One, we can have J equal to 0, K equal to 1. That way we ensure that Qn plus 1 is 0, that is the output just after the active edge. Or we can have J equal to 0 and K equal to 0. That will make Qn plus 1 equal to Qn, and since Qn is already 0, Qn plus 1 will also be 0. What it means is we must have J equal to 0 and our K can be either 0 or 1. That is, K is a don't care condition. And that is how we indicate the choice of J and K. So J is 0, K is X, for Qn to be 0 and Qn plus 1 also to be 0. Now let us consider this next case. If Qn is 0 and Qn plus 1 is required to be 1, then what can we do? One thing we can do is have J equal to 1, K equal to 0. That will force Qn plus 1 to be 1. The second option is we see that this Qn is toggling here, and therefore we can have this last J and K values. That means J equal to 1 and K equal to 1. So these are the two options we have. That means J must be equal to 1 and K is a don't care condition, like that. For Qn equal to 1 and Qn plus 1 equal to 0, we can either use this row of the table or we can use this row in which Q toggles, and that suggests that K must be equal to 1 and J is a don't care condition, like that. And finally, for Qn equal to 1 and Qn plus 1 also equal to 1, we can either use this row or we can use this row in which Q does not change. That gives us K equal to 0 and J is a don't care condition, like that. So this is the complete table, and it tells us what J and K should be if Qn and Qn plus 1 are given. And this table can be used for designing a counter with a specific sequence, and we will take a look at an example soon. Alright, what if this flip-flop is a negative edge triggered flip-flop rather than a positive edge triggered flip-flop? The table would be identical except for the active edge. So here we will have a negative clock edge rather than a positive clock edge. Apart from that, these entries will remain identical. Let us take up this design problem now. Design a synchronous mod 5 counter with the given state transition table. What is the meaning of synchronous? That means the same clock is going to all flip-flops. We have 3 flip-flops here. Their outputs are Q2, Q1, Q0, and the corresponding inputs are J2, K2, J1, K1, and J0, K0. And here is the state transition table that our counter must satisfy. We start in state 1, which is Q2 equal to 0, Q1 equal to 0, Q0 equal to 0. Then state 2, 0, 0, 1, followed by 0, 1, 0, 0, 1, 1, 1, 0, 0, and then back to 0, 0, 0. Okay, here is an outline of the method that we will use. First, let us see the meaning of state 1 changing to state 2. What does that mean? That means we are going from this state to this state. That is, Q2 is changing from 0 to 0, Q1 from 0 to 0, Q0 from 0 to 1. That is the meaning of state 1 going to state 2. Alright. Now what we do is refer to this table on the right hand side, this one that we saw in the last slide. Now for Q2 to go from 0 to 0, we look at this entry, Qn equal to 0, Qn plus 1 equal to 0. Then we require J2 equal to 0 and K2 equal to X, and so on. When we cover all transitions in the left table, here we have the truth tables for J0, K0, J1, K1, and J2, K2 in terms of Q0, Q1, Q2. And the last step is to come up with suitable functions for J0, K0, J1, K1, J2, K2 in terms of Q0, Q1, Q2. And this can be done with K-maps, as we have seen earlier. If the number of flip-flops is more than 4, then we cannot use K-maps, and then other techniques can be employed. Alright, let us get started. Here is our table for J and K from given Qn and Qn plus 1. Let us start with the first change, that is from state 1 to state 2, and let us consider Q2 first. Q2 is changing from 0 to 0. We look at this row, Qn is 0, Qn plus 1 is also 0, therefore J is 0, K is X. J is J2 here and K is K2, so therefore we write 0 and X over here. What about Q1? The same transition, so 0X again for J1, K1. What about Q0? Q0 goes from 0 to 1, so we look at this row of the table and find that J0 must be 1 and K0 must be X, like that. Let us consider the next transition now from state 2 to state 3. Q2 goes from 0 to 0, so we have 0x for J2, K2. Q1 goes from 0 to 1, so we have 1x for J1, K1, and Q0 goes from 1 to 0, so we have x1 for J0, K0, and so on. And proceeding in that manner, we now have the truth tables for J0, K0, J1, K1, and J2, K2 in terms of Q0, Q1, Q2, this table here. The next step is to find logical functions for each of them. And note that we have not tabulated the J and K values for those combinations of Q0, Q1, Q2 which do not occur in the state transition table. For example, this combination Q2, Q1, Q0 equal to 1, 1, 0 is not present over here. So therefore these combinations can be treated as don't care conditions. Now in this table we have 5 distinct states out of the 8 binary numbers that we can make up with 3 variables, and therefore there would be 3 don't care conditions. Here are the K-maps for J2, K2, J1, K1 and J0, K0 which are derived from this table that we saw in the last slide. And let us take one of these as an example and see how the K-map is constructed. Say we take J2. Now for state 1 we have Q2, Q1 equal to 0, 0, Q0 equal to 0. That means we have this column and this row, and J2 is 0. So we write 0 over here. Next we have column equal to 0, 0 and row equal to 1, and J2 is 0. So we are talking about this column, this row, and again J2 is 0. State 3, the column is 0, 1, row is 0, and J2 is 0. So column 0, 1, row 0, again J2 is 0. State 4, column 0, 1, row 1, and J2 is 1. So column 0, 1, row 1, and J2 is 1. And finally for state 5, column is 1, 0, row is 0, and J2 is X. So column is 1, 0, row is 0, and J2 is X, like that. Now these other combinations, these three, do not occur in the state transition table, and therefore J2 is X over there. We don't care what J2 is. And similarly all other variables, and so on. Now these three X's have been marked in a different color just to distinguish them from this other X's which come from this table. Alright. Now once we have these K-maps, we can go ahead and minimize these functions J2, K2, J1, K1 and J0, K0, and then come up with expressions for each of them. And here are the minimized expressions for J2, K2, etc. J2 turns out to be Q1, Q0, and you can verify. K2 is 1. In the map for K2 there is only 1, 1, and all others are X's, and we can assign 1 to each one of these X's so that this entire function is simply 1. J1 is Q0, this term here. K1 is also Q0, that one. J0 is Q2 bar, this term, and K0 is 1. So if we implement these functions, then we should get a counter which follows this state transition table. And one more final point, we will assume that a suitable initialization facility is provided to ensure that the counter starts up in one of the 5 allowed states. For example, Q2, Q1, Q0 equal to 0, 0, 0. And if that happens, then the counter will simply keep following the counter sequence given in this table. Alright, so here is our final implementation. These are the flip-flops we saw in the last slide. And now in addition, we have made connections for J2, K2, J1, K1, J0, K0 such that they satisfy these equations which we have seen in the last slide also. So let us check whether the implementation is correct. J2 is expected to be Q1, Q0. Here is J2 and there is an AND gate here. One input is Q1, the other input is Q0. So J2 is indeed Q1, Q0. K2 should be 1. Here is our K2 and that is tied to 1. J1 should be Q0, that is J1, and that is connected to Q0. K1 is also Q0. J1 and K1 are tied together. J0 should be Q2 bar. J0 should be Q2 bar. So we have Q2 bar here, and K0 should be 1. So K0 is tied to 1 here. Here are the simulation results, and the circuit file is available to you, so you can check it out. Even better, you can go to your digital electronics lab and hook up this circuit and see if you get the same counter sequence. Alright, now let us verify whether our counter operation is correct. We start with Q2, Q1, Q0 equal to 0, 0, 0. And after the first active clock edge, which is the rising edge here, since these are positive edge triggered flip-flops, we get 0, 0, 1. Then we have 0, 1, 0. Then we have 0, 1, 1, followed by 1, 0, 0, and then finally back to 0, 0, 0. So you can go back to the previous slide and make sure that this is indeed the sequence that we set out to achieve. Alright, one more final remark. Note that the design is independent of whether positive or negative edge triggered flip-flops are used. So the same connections are also valid if we replace these flip-flops with negative edge triggered flip-flops. The only difference that will happen in the results is that the transitions will now happen at the negative clock edge. Let us now see how we can combine two different counters and what does it buy for us. Okay, so here is counter 1 with its own clock called clock 1, and it is a mod K1 counter, and we will take this example where K1 is 4. So this counter would have 4 different states. These are the outputs, and it's not really important what N1 is right now. Here is the second counter, counter 2. It has its own clock called clock 2, and it is a mod K2 counter, and we will take this example where K2 is 3. So this second counter has 3 distinct states, and now let us see how we can combine these two counters. Alright, so here is our counter 1. It's a mod 4 counter, so it has 4 different states called 1, 2, 3, 4 here. This is the clock for the counter, which is called clock 1. In the first clock period, the counter is in state 1, then it is in state 2, 3, 4, and then back to state 1, and then that repeats. What we do now is to use some decoding logic to derive the clock for the second counter, which is called clock 2 here, from the outputs of the first counter. And here is an example. So this is what clock 2 may look like. It is 1 when the first counter is in state 1, otherwise it is 0. So it is 0 when the state of the first counter is 2 or 3 or 4, and it is 1 again when the first counter is in state 1, and so on. Now this clock 2 serves as the clock for the second counter, which has 3 states. So with every clock pulse, the state of the second counter changes. So here it is 1, then it is 2, then it is 3, and then back to 1. So we have 2 different states here. State for counter 1, which is indicated by blue numbers here, and the state for counter 2, which is indicated with red numbers here. Let us now look at the combined state of the entire circuit. It has got 2 components: the state of counter 1 indicated by the blue numbers here, and the state of counter 2 indicated by the red numbers here. In this interval, counter 1 is in state 1, counter 2 is in state 1, so we have this combination here. In this interval, counter 1 is in state 2, counter 2 is in state 1, so we have this combination here, and so on. And let us now try to figure out the modulus of the combined counter circuit. What is the meaning of modulus? That means the number of clock pulses after which the combined state repeats. So let us start with 1 1, then 1 2, 1 3, 1 4, 2 1, 2 2, 2 3, 2 4, 3 1, 3 2, 3 3, 3 4, and now we are back to 1 1. So after 12 clock pulses, the combined state is repeating. So therefore this is a mod 12 counter, And this 12 of course came about because K1 is 4 and K2 is 3. So 12 is simply K1 times K2. So the combined counter is a mod K1 K2 counter. So that is the conclusion from this figure. Let us look at an example of combining two counters using the approach that we saw in the last slide. Here is a mod 2 counter, here is a mod 5 counter, and using these two counters we are going to make up a mod 10 counter, 2 times 5. Alright. The first counter is simply a JK flip-flop with J and K tied together, connected to 1. So therefore this Q0 is simply going to go on toggling as shown over here. This second counter is a mod 5 counter, and in fact we have seen this circuit earlier, and the associated waveforms are shown over here. It has this sequence 0 0 0 for Q2 Q1 Q0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, and then back to 0 0 0. So this is its own clock, and now what we are going to do is to derive the clock for the second counter, this one here, from the output of the first counter. And in this case we don't really require any decoding logic because this Q0 itself can serve as the clock for the second counter. So let us see what happens when we do that. So here is the combined counter. This is the mod 5 counter, and its clock is now coming from the output of the first counter, which is a mod 2 counter. And now let us verify that the modulus of the combined counter is indeed 2 times 5, that is 10. Here are the waveforms. This output, the output of the first counter, has been renamed as QA now, and that is what it looks like. With every clock pulse it toggles, and these are the outputs coming from the second counter, Q0, Q1 and Q2. This is the first clock period, this is the second clock period, third, and so on. And we see that this state, that is 0 0 0 1, appears again at this point 0 0 0 1, and therefore the modulus of this counter is 10, because after 10 clock periods we get the same state again. Let us now consider another approach to combine two counters, a mod K1 counter and a mod K2 counter, to obtain a mod K1 K2 counter. Here is the same example again. Our counter 1 is a mod 4 counter and counter 2 is a mod 3 counter. This is our counter 1, and that is clock 1. It has 4 different states marked with these blue numbers, and after 4 clock periods state 1 appears again, and so on. Here is our second counter, counter 2, and that gets the same clock as clock 1. So clock 1 and clock 2 are the same signal now, and let us see what happens. So this is our clock 2, the same as clock 1, and these are the states of the second counter. It's a mod 3 counter, so we have 3 different states, and after 3 clock periods this state 1 appears again, and so on. Alright. Here is the combined state. In this interval our counter 2 is in state 1, counter 1 is in state 1. In this interval our counter 2 is in state 2, counter 1 is in state 2, and so on. And now let us take a specific state, say 1 1, and see when it appears again. So we start with 1 1, then 2 2, 3 3, 1 4, 2 1, 3 2, 1 3, 2 4, 3 1, 1 2, 2 3, 3 4, 1 1. So now 1 1 has appeared again, and that has happened after 12 clock periods. So therefore the combined counter is a mod K1 K2 counter. K1 is 4, K2 is 3. So therefore the combined counter in this case is a mod 12 counter. Alright, let us now look at an example, and these counters, our counter 1 and counter 2, are the same as before. This is a mod 2 counter and this is a mod 5 counter, and now what we are going to do is to apply the same clock to both of these counters and see what happens. So here is the combination. The same clock now goes to counter 1 as well as counter 2, and here are the waveforms. This output is called QA, and the outputs of the second counter are called Q0, Q1, Q2. So this waveform is for QA, then we have Q0, Q1, Q2. Now let us start with the state 0 0 0 0 and see when it appears again. And we see that it appears again, not here because we have 0 0 0 1 here. It appears again over here. We have 0 0 0 0. So that means this state has appeared after 10 clock periods, and therefore this is a mod 10 counter as we would expect. This is a mod 2 counter, this is a mod 5 counter, and therefore the combined counter is a mod 10 counter. In summary, we have seen how to design a synchronous counter satisfying the specified state transition table. We have also looked at how two counters can be combined and what is the modulo number of the resulting counter. That is all for now. See you later.